The first thing, my name is, I'm probably the guy that is called Ivan and doesn't speak Russian, although my badge currently says Alexander Zaitsev, which is so cool. So for the people who don't know me, although I've been here, this is my third CoreHard, and I've been to C++ Russia at least a dozen times. As all of the speakers at the conference usually are, I'm an independent trainer and consultant. I'm also a KD developer. For people who don't know KD, KD is one of the largest C++ free software project in the world. I'm one of the library developers there. I also wrote an interesting book on practical functional programming. It's not said in the title, but it is practical. It's not academic, even if I have a PhD, etc. So the book is definitely not the PhD style book. And ignore the part where I teach at the university. Okay, so as you all probably know, this is the quote with which I start all of my talks. So make your code readable, pretend the next person who looks at your code is a psychopath and they know where you live. So this is a quote by one of the great functional developers and, let's say, fathers of many things in Haskell, called Phil Varro. You should Google the guy out. He gives great talks, and he usually wears a Superman costume with a lambda instead of DS as a Superman at a conference. And he's quite an older guy, so it kind of looks really interesting to see an older professor in a Superman costume. Okay, so let's start. Today's topic is going to be about DSLs, languages that we design for a specific domain, which is kind of what the name says. So we have a couple of really famous ones like SQL, the world's most hated domain-specific language. We also have the language to define other languages, which I always forget the name of. And we have regular expressions. And for each of those are specific domains. We have data extraction, SQL. We have language design, so a language just for that. We have string pattern matching, and we have a language just for that. Regular expressions are not meant to query the database, for example. So these are all normal DSLs. And usually for normal DSLs, you invent some syntax, then you invent semantics, you write a parser, and everything else. Today we are going to talk about a different type of DSLs called embedded DSLs. So the languages for which you don't invent a syntax, you're kind of reusing the syntax of the host programming language, in this case C++. So if we wanted to create a DSL in C++, that would mean that we need to leverage on the syntax of C++. We can't invent our own. So we can have a syntax based on dot something, the usual object-oriented style. We can use and abuse operators that are available to us, and obviously, whenever we need a list of something, we will need to use either braces or normal parentheses. So we will kind of have a limited type of syntax that we can create. So recently we've got, again, it's always weird to me to say recently we got when it's something that is going to happen in C++ 2020. But let's say we got a new operator called a spaceship. So, and we are all excited by the new operator. Now there are different languages that are not C++, which allow you not to have only the spaceship operator, but you could have operator, a boat on a river next to a mountain, and some intermittent clouds with the sun. Obviously, in C++, we can't create operators like this. Now, some people would say it's a drawback. I would personally say it's not, because one of the languages that allows you to do stuff like this is Haskell. And although we all love Haskell, obviously, because we are C++ developers, for some reason we need to love Haskell. When people see that they can abuse operators like this, they create unusable libraries, which are obviously perfect for them, because they all know, and all the operators they defined are completely logical. But for most of the people that didn't write the library, they're not. So in C++, we kind of have something of a sane place in the world. We are not completely let's say C++ is not completely unusable for DSLs, and it's not overly powerful for DSLs, so we are kind of in the perfect middle. So let's start with a basic example. So we have an object, we have a name, username, name, surname, and age, and we want to update a few fields of that object, and the second one throws an exception. What do we get? We get an object that is just partially updated. Usually in C++, we tend to try to be safe, to have strong safety when exceptions occur, which means that if an exception occurred, then we should have performed no updates. And if there isn't an exception, all the updates should have been performed correctly. So it's kind of like transactions. Now, one of the idioms that allows us, for example, to implement the assignment operator in a safe way is the copy and swap idiom. So instead of updating the current object, we are creating a temporary copy of the original. Then we do some changes. And then we just say swap the temporary data from the temporary with us. What happens if the copy constructor throws, the temporary object is destroyed, our current this is not changed. If that one didn't throw, swap should never be able to throw. Swap always needs to be defined as a no-throw. And returning star this also cannot throw. So this allows us to have strong exception safety. How can we apply it to our previous example? We can say auto temp user, and then update temp, update temp, update temp. And when all the updates are successful, just call swap. Now imagine that we need to do this in a lot of places. Always creating a temporary, always doing the swap at the end, etc. It would be probably much nicer if we could just remove a lot of syntax from this and invent our own DSL that will allow us to create transactional updates to some of our objects. Now, if you see this, does it look like C++? Kinda. It's yes and no. It's obviously not normal C++. But it still doesn't use any of the syntax that C++ compiler doesn't understand. So what does C++ compiler see here? It sees something called with user, and it knows that with user has the call operator, because we are using normal brace parentheses to pass it a few values. And all of those values, again, if we deconstruct the AST, we are going to get the operator equals, and what was on the left-hand side of the operator, and what was on the right-hand side. So this is what the compiler would see. So when we know the AST, we can start implementing our classes that will implement the AST. So for the transaction itself, we just need something that is able to hold a reference to the object that we need to update. So we can call it a class transaction, and on construction, it's going to get the object that it needs to update. So at the moment, we have implemented the with user. The next step is to implement the call operator, which will take a list of actions. We still don't know what actions are, but at least by defining this with a constructor and a call operator, we have implemented all the syntactical parts of our DSL that we need. So the next step, how to implement something like this. Obviously, here we just need to be able to store two values. We need to store which field we are going to update and which value we want to assign to that field. So we can create just a structure called update or action or something like that, and it just is a dummy class that has a member value called member and the member value called value. So member is going to be which field we are going to update, and the value will be what value we are updating that field to. Now the important thing to note is that this block has no idea that the user exists. it doesn't know on which user it operates on. This is a subtree of the AST and doesn't care about anything that is above it. It's a context-free AST. So now how do we get an instance of this update thing? We can just create a class called field, and that field will just be, again, a really, really dummy class that just remembers a member. Okay? So if we know the member, we can just create the operator equals to, which creates the update action because we just got a value as well. Now, in functional programming, this kind of can be seen as currying. If we have two values and we have the block that needs two arguments to be invoked, and we have just created something that is that can be created from a single value and then afterwards gets the second argument. So we have implemented the operator equals. So we have implemented the green rectangle. The Martha, Jones, and 42 are just normal values, so strings and integer. So we have kind of implemented all the syntactic parts of our DSL. Now the question is, if we want to support the DSL that we had in the original slides, we need to define what name is as a freestanding variable. We need to define what surname is as a freestanding variable. So we can just say field name and then provide it with, for example, ampersand user t : name. Or something like that. So we just need something global that C++ can see when we write name equals something. Because C++, again, because of the syntax, it cannot know that that name belongs to anybody. It just needs to be a freestanding dummy object. Alternatively, if you don't want to define these things for every single property that you want to be able to update, you can use the dirtiest part of C++ and C, which is obviously macros. So we can define a macro, which this works since C++ 14. So for each name that somebody gives you, you are essentially returning a lambda, which gets an object by reference and returns a reference to object.name. This is a trick that is often used when you have pointer to overloaded member functions or anything similar. When you don't want to have the huge sausage of characters to define what you're calling, if you just want to write a name of a member variable or of a member function. So this is kind of like macro generic programming. The problem with this is that it's going to force us to change our syntax a little bit. Instead of being able just to write name equals something, we'll have to write field of name equals something. Okay? And obviously, field of name will create the lambda and pass it to our fancy object that will later be able to update the object. And the reason why I mentioned this is possible since C++ 14 is the return type autoref for a lambda. Otherwise, it would have been quite fine for C++ 11 as well. So we have implemented this. We just now need to implement the semantics for our transaction object. So far, we've just thought about syntax. We didn't even consider what a transaction is. When we need to implement semantics for a language, then we need actually to reason about what the syntax means. So we can have different approaches. We can, depending on your project, whether you're using exceptions, error codes, or std expected, std optional, etc., you can define different ways of how to denote when an update has failed. The most simplest one is we can say that an update succeeded if it returns true, and that it didn't succeed if it returns false. Obviously, the same would work with exceptions or anything else. So if we have updates which return us true or false, our operator, which gets a variadic template, a variadic number of arguments containing update objects, we need to create the temporary object. We need to pass through all the updates perform the updates on the temporary object. If all the updates succeeded, then we do the swap, and our operator can return true because it succeeded. Otherwise, we don't do any swaps. We just say return false. Now, one of the really amazing and probably incomplete features of new C++ standards are the fold expressions. If we had a variadic number of arguments in a template in C++11, we would need to handle this with recursion and really a lot of boring boilerplate code. With fold expressions, we can just say, take the update object, apply it to temp. Obviously, because it's perfect forwarding, we need to forward the update object. And then use the fold expressions and just conjunct all the return values. Okay? So we have the updates object. The updates as a pack will be expanded to several updates. It will be, let's say, update 1 on temp, and then update 2 on temp, and then update 3 on temp, etc., etc. So this will be true if and only if all the updates return true. In that case, we can just do temp swap with muser and return true. Otherwise, we just return false. So fold expressions are amazing. And there was a talk earlier about speeding up compilation. One of the advices was to remove template metaprogramming. If you are not willing to give up TMP completely, this is at least a halfway there. Instead of having recursion and everything else, this simplifies the compilation quite a lot. Again, I don't have benchmarks. You can ask some of the members of the audience. So the DSL that we've just created is a perfect, beautiful DSL. Not because it's powerful or anything else. It's beautiful because it's simple. It's easy to understand when you see the code, you understand what it does. And most of all, the most beautiful part is that it's context-free. And that's the reason why it was quite short to implement. Now, when you implement your own DSLs, you should always strive to create something that is context-free. But since this talk would be kind of incomplete if I just said, OK, that's all, let's now see what tools we have to implement a little bit more advanced DSLs, even if they kind of appear simple at first. So who knows this syntax? What does it look like? I meant something from C++20 by Eric Niebler. So this is the syntax that ranges use. On one side, you have a collection. So let's say a source of data. And then you, just like in Bash, you pipe the transformations to that collection, and then you get a result. Now, this library is not really range. It is something that I've been working on and talking quite a few times, I think even at CoreHard. In essence, reactive streams. So unlike ranges, you also have the collection or the source or the producer of the values. But at the end, you always need to have a consumer, somebody that is listening to those values. OK? In essence, if you have values that are emitted, but nobody is here to listen to them, then there is no point. It's like that philosophical question, if a tree falls in the woods, does it make a sound if nobody is there to hear it? In this case, the answer will be no. So we need to have the source, we have some transformations, and then we have the destination or the sink. And we want to implement a DSL behind all of it. The naive thing would be to think that AST looks like this. Because we have an item, and then we just have a pipe. If the AST looked like this, we could just say, OK, let's create an expression template, which already contains a chunk of nodes. And it has operator pipe. Whenever we add a new node, we are going to return a new expression with that node added. So this would be quite simple if this was the case. Now, the question is, how would we connect things? Because the pipe operator is left associative, we would either need to use std function, so some kind of type erasure when connecting the continuation function, so the nodes that are on the right-hand side of the pipe operator, or we would need to go to connect from right to left. So we could connect from right to left. We could use some operator like greater, greater, equals, or any right associative operators in C++, which would kind of be ugly. It would look a lot like Haskell, but it wouldn't look like C++. So obviously, if we have a left associative operator and we need it to behave like right associative operator, what we need to do is create expression templates instead of evaluating the pipe operator immediately. So we could just say something like this. Whenever we have a pipe, just concatenate the right one. So we are not evaluating the pipeline, we are just storing all the nodes inside of a tuple. The problem with this approach is that, just like ranges, whenever you define pipelines, it would be really nice that you can refactor and say, okay, this part of the pipeline, I want to call it like this and put it in a variable. The first part of the pipeline, I want it to be called this and put it into a variable. And then just at the end, connect all those variables. This means that we can have quite different pipeline operators. For example, in the auto user names, users is a source, so something that emits values. And if you pipe it to a transform, you get a new entity, which again emits values. It emits just transformed values, but it's still something that is a source of data. If you just have transform and remove if, those are two transformations. We don't have a source of data, we don't have a destination for the data, we just have the composition of two functions. So it's a completely different meaning. Applying a function to a value or composing functions is kind of different. And then we can compose all of these again with the pipe operator. This is something that wouldn't be allowed in much more, let's say, mathematically oriented languages like Haskell. You would need to use different operators for composing functions and for applying. So our AST kind of looks like this, an arbitrary binary tree, which is a level of complexity which you should always strive to avoid. But if you can't avoid it, then you just need to deal with it. And all of the nodes, so all of the results of the pipeline, can be different types. If it's a source and it has a transformation, it's a new source, so the blue dots. If it's a destination for the data and you just prepend a transformation to it, it's again destination for the data, right? And if you just have two transformations, then the composition is a new transformation. It's not a source, it's not a destination. And if you have both the source and the destination, then you cannot pipe it to anything else because you have a complete pipeline. You have the source and you have where the source leads. So we have 4 different types for our nodes, for the results of the pipe operator. Now we could use some object-oriented techniques as presented in the previous talks and use virtuals, etc. But if we called a virtual function for each of the transformations, it would be a little bit slow. So we will try to slow down the compilation as much as we want, but we want to speed up the execution. So no virtuals. What we can do is, okay, this is just the general expression for a binary tree AST. What we can do is tag our types. Instead of creating different types for each of those, we can just create a single type and then define a nested type def that says which category that type belongs to. So for each of the nodes in our AST, instead of just having the left and right subtree, we are also going to remember, are we a source or a sink or we are a transformation? Is this fine? This is something that is commonly used in the STL for iterators. Iterators have their own tags, etc., whether they're random access or forward, etc., etc. So this is not an uncommon thing to see in a C++ library. So we then can create a meta function that for a given node, for a given AST, it gets whether that that part of the AST is a source or a sink or a transformation. And this is something that you should become quite accustomed to. So one of the new meta functions that we got in the C++ standard is remove cvreft, which kind of like does the same thing like stddk, apart from, well, it does exactly the same as stddk, just the good parts. So it doesn't decay arrays to pointers, etc. It just does the removal of constant, volatile, and the reference. So we are removing all those, let's say, additional things around our type and extracting what node type tag returns. And now our expression is not, as I said, it's not going to be just left and right subtree. It also has the tag which will tell us which type of the expression it is. And now one of the most beautiful things until concepts arrive, and one of the most confusing ones, when we have a meta function like node category, we can use it to do some compile time introspection, to check whether some type has a nested node category or not. So we can use the std-detected T. It's usually called the detection idiom. There were a couple of talks about that in previous CPPCon, C++ Russias, and maybe CoreHards. The detected T is going to return you a type, so the result of the detection. And isDetectedV is going to return you true compile time, true if something has been detected on the type, and otherwise returns false. So in this case, we are writing a meta function, which at const per bool meta function, which checks whether something is a node in our AST or it's not. What is a node? A node is, let's first check, do we have a defined node category on it? If we don't, then it's not a node. Fair enough. Okay, let's move on. If const expr is the thing that we've detected as the tag, the same as complete pipeline. So the first was it's not a node at all. The second one, it is a node, but it's a complete pipeline. So we cannot really consider it a node in our AST. So also we are returning false. Because if it was a node, we could just pipe it to something else. And otherwise, we return true. So this is a nice way to write const per bool meta functions in C++ 17. So we can use this const per bool meta function, which I'm trying not to call a concept yet. In C++ 20, you could define a concept that does exactly the same thing. And you can use it to restrict your template, your generic functions, just to work on your nodes. So instead of when you create a normal operator pipeline and just say it's templated on both arguments, it would kind of match any kind of type, right? This requires that both left and the right are nodes. Obviously, require is a macro, and behind require is enable if. But nobody in their right mind would write enable if directly. You should always just wrap it up in some kind of macro that looks much better than enable if. So this operator will be invoked only if both of the arguments are a part of our AST type system. So let's now implement the pipe operator. If the left argument is not a producer, so a source of data, and the right one is not a consumer or a sink, that means that we got two transformations, and we are going to return a new expression which has transformation node tag. Okay? If the left one is the producer and the right one is a transformation, then we are returning a new expression which has a tag producer. The same if the left one is not a producer, but the right one is a consumer, then we are returning a new consumer. And the last one, if we have both a producer and a consumer, we are returning a complete pipeline. Okay? So far, in the last one, this is the only value that is not going to return true for is node. So we have a complete AST. Now the question about evaluation. Really? Can I have an extended a little bit time? Because, you know, I started a really late because Polukhin. Damn. Okay, so as I said, because of the std function thing, we need to be able to evaluate things from the right to left. So I'll have to kind of skip. You know binary traversal of a binary tree, right? So if you need to do it at compile time, you just create, collect, it can be a const expr, and then just traverse through the left subtree, through the right subtree, convert them to two tuples, and just do the tuple cat. So I'm assuming that for any binary tree, which is a compile time binary tree, we can just flatten it out to a single tuple. So as I said, we have two choices. We can connect left to right, which is a problem because we would need some kind of type erasure. And we can do connect right to left. Now we don't have a problem with right to left because now we have a tuple, we can traverse it in any order that we wish. With left to right, the benefit is that it's easier, and it's easy to pass the value type around. So when we have a pipeline, the middle node, it should probably know what types of values it can receive. If we connect everything from right to left, the middle node cannot know anything about its left-hand side. Okay? So in that case, we don't, in this case, in left to right, we can pass the value type from the source to the transformation up to the sink. But the problem is that because of the continuation functions, we need to use some type erasure. If we go from to right to left, the good thing is that it's not, it doesn't need type erasure. The problem is that we have no way to pass the value type. So for example, if you wanted to debounce something or to cache events, the cache object needs to be able to know which types of that it needs to cache. So you would need to write a debounce of std string because the language, the library cannot deduce it for you. So we kind of want the best of both worlds. And the only answer is to do both. Do both left to right and right to left. So how can we do that? First, we need to go feed forward to deduce all the value types, which means that we need a member, let's say, a member meta function in all of our transformations to which we can give a value as an input and a type as an input, and it returns us which type it's going to emit. So for example, if you have a filter node, if it receives a string, filter node will return that it emits a string as well. If we have a transformation that transforms with std to string, then if the input type is int, this meta function needs to return std string. So by using this function, we can now just go feed forward through our tuple and deduce for each of the nodes which type of a value it's going to receive. And obviously, we can create a meta function that just wraps the type name, data colon, template, etc., etc. In C++20, most of these type names and templates in these kind of places will not be needed anymore. So preparing the 5 minutes one, okay. So when we want to do the folding, in this case, we need, while folding, we need to remember all the previous values, so all the previous already processed nodes, And we need to be able to remember which is the last deduced type, so that we can tell it to the next node, you're going to receive this type. So something like this. For initially, the last deduced type is nothing, it's void, and previously processed nodes are still nothing because we haven't processed anything. When we encountered a source of the data which emits strings, we are just going to say, okay, we just processed you, and we deduce that you just send us strings. The next step, okay, we have a transformation which converts string to JSON. When we process that one, we've told the second node, okay, you're going to accept strings. The node told us, okay, I'm going to give you JSON, and we have stored it as the last deduced type. The next step, JSON to bookmark, okay, etc., etc. So in each step of the folding, we are processing and telling a node, okay, you're going to receive this value, and the node gives us the value that it's going to emit. And in the end, when we have passed through all and found a sink doesn't emit values, so the extra data will again be null. Now we can forget the deduced types and just use the enriched nodes that we've just passed through. And again, this can be done with fold expressions quite easily. The only problem with fold expressions is that they only work with operators. So you need to find an operator to abuse. And in this case, I chose to abuse the percentage because I found it the least used of all operators in all C++ land. So usually when you see percentage, it kind of signals you, okay, this is not a normal operator. So in this case, we have the initial context with void and an empty tuple, and just folding through all the nodes. Now, that would be the case if we actually had the nodes as a template pack, which we don't. We have a tuple. So we need, if we want to use the fold expressions, we need to have separate items as template arguments. We can't have just a single tuple. So in this case, we would need to use something really cool and evil called std_index sequence, which allows you to generate a series of compile time integers. So you're going to get size t idx, which will be 0, 1, etc., as many items as you have in a tuple. And then you can use this is the reason why I usually give talks from my laptop. Just a comment to Anton, if he's here. We can use std_get and index to get a certain field from a tuple. And this is it. We can just call this function, create an index sequence for the exact tuple, and it's a little bit of a problem because we need to have a bit of boilerplate and indirection, but all of this indirection is going to be dealt with by the compiler. So we have the left to right thing, and now we just need to do the opposite. And when we evaluate nodes, we can just use the wrong way fold expressions and define another percentage operator that this time does continue with continuation. Okay, I'm going to fly over the following slides. So usually when you deal with any template stuff, you get a lot of beautiful poems from your GCC or Clang. So all the compiler errors are awful. The first thing that I would advise you to do is to declare this macro and assert that all of your types are value types unless you have a reason not to. So by default, just like by default, use const everywhere. By default, use this everywhere. And if you actually need the reference type, you can say assert value type for t and then use tref to be more explicit. This way, you will not have problems with accessing t : something, and then it turns out t is a const ref or something else. The next thing is use printf debugging for template metaprogramming. So declare a variadic class which is not implemented called print types, And then you can just say to your compiler, print types of std vector bool : reference. When you try to compile, what will happen? The class is not implemented anywhere, so it's a hard error. The compiler will print out, okay, complete type. You're trying to declare print types of std : bit reference. So you're getting exactly what type the compiler sees from your request. Now, obviously, the usual problem that people see in this is that it allows you just to print once. Because as soon as the compiler finds print types, it's a hard error and it stops. If you're using Clang and you want to be able to have a lot of values to print out in different places, you can use a really awful trick and implement a class, I forgot the curly braces, and just mark it as deprecated. Then Clang will report each of the warnings for deprecation with exact beautiful types that you wanted to print out. And this is amazingly useful because whenever you do template metaprogramming, you have really huge problems that you assume that type T is something, and the compiler knows that it isn't. And then you have a huge error. With this way, you can correctly know exactly what your type is. The problem is that with ASTs, those are huge trees, huge types. And we've seen in today's keynote that it can be kind of unreadable. A lot of things, a lot of text in a few lines. For that, I advise you to create some kind of dirty script which converts all the less than and greater than to normal parentheses and push everything to Clang format. Just write a script that gets that output from your compiler, whatever you put into print types, replaces the parentheses and does some sanitation like basic string to string, etc., shortening out of things, and then passes everything to Clang format. Then you can get quite a readable AST output. In this case, when you see this, okay, it's an expression. Okay, quite logical. Then we have an expression of void, which tells us it's a complete pipeline. Expression of producer, so it's a node that produces values. It is then connected to an expression of producer, etc., etc. So this is the output before we have flattened out the tree. After the flattening out, it will just be an expression of this node, this node, this node, this node, this node. And with the deprecated trick, you can actually, when you compile your program, you can see all the types as you go through them, just like you do with normal values with your normal program. And you can immediately know, okay, this step is wrong. This step returned me something that I didn't expect. And that's it. I hope I haven't gone through the, okay. Thanks. Okay, the power. Okay, any questions?
So I wonder where is the line between an embedded DSL and an API, how to differentiate them?
That's an amazing question. So if I need to repeat it, where is the line between a DSL and the API? I have no idea. In essence, from my not really a strict definition, but as soon as you start using operators, then I wouldn't call it a normal API. But I don't think that, I think that the line is blurred.
Okay, thank you.
But it's a really nice question.
Well, really great talk.
Thanks.
Yeah, I enjoyed it very much. I just wanted to say that it's awesome. and yeah, when you were speaking about embedded DSLs, I was thinking about like the main language that is intended to create new languages, like Lisp. What about new dialects of it? Do you like it, like Racket or something like that?
Okay, I can't really start talking about Lisp and stay politically correct. So I'm going to skip this question. It's a nice language. That's all I'm going to say. No more questions?
So sometimes people talk about deep embedded languages and shallow embedded languages, depending on how you represent it within the host language. And while you did not have time to talk about this, but I wonder what are your preferences?
To be honest, I haven't investigated that much of what people usually do with DSLs. Okay. This is something that just I had to come up with in my project. And DSLs, depending on the language, obviously, can have an enormous impact on the language. And for example, this is just, let's say, a library. You might have said API. With languages like, let's say, Erlang, you have so much power to actually create a completely different language to program Erlang. And I do like that. I do miss that in C++. At some point, we will get meta classes and meta other stuff. So we will be able to do the same. But I don't really have any opinion on that.
So what I was wondering about, do you think the DSL should reflect, so for example, with this pipeline, should it reflect the same semantics as you define it, or should you be able to do, for example, some optimization transformations like...
Okay. So I would say that optimizations should be possible. In this case, since you have an AST, when you traverse over it, you can do the optimizations. In the ranges library, for example, it would be quite cool to have something like sort take 10, and that sort then needs to deduce, okay, I can be a lazy sort and just sort the first 10 elements. So that I would say that's obligatory for more advanced DSLs.
Thank you.
Thank you for this talk. I have a question about the part where you were using std get and std index sequence or something like that. Could you use std apply there, or it is not enough? Maybe you could simplify, because it was like quite a lot looking like std apply, because yeah, you also pass.
Okay, do you remember the number of the slide?
No, you're too fast.
Well, don't blame me. I got signals from...
Okay, also blame pollution.
Ah, for the love of God.
Yeah.
This one?
Yes.
How do you mean std apply?
Maybe so we were using percent like to make why do we need, first of all, this percent sign? Like,
so the percent here is because fault expressions need an operator, and we are essentially simulating std accumulate over values in a tuple, and not doing, let's say, value computation, but using std accumulate for type computation. So I don't see how this could benefit from std apply.
Okay, thanks.
But I think in some of the slides, maybe std apply could have been applied. Maybe I just switched to the wrong one, intentionally or not. Anyone else? Acrobat Reader? Okay. Okay, if there are no more questions, you can find me on Twitter. You can send me an email, which was in the first slide, I think, or you can find me at the beer party, at least for a short period of time. Thank you.
Большое спасибо, коллеги. Сейчас я еще секундочку. Большое спасибо, коллеги, что вы все еще с нами. Это настоящий подвиг. Так долго слушать разнообразные доклады по C++. Мозг обычно плавится гораздо быстрее, но вы выдержали, несмотря на температуру. Так что еще раз вам большое спасибо. И не менее важная часть – это неформальное кулуарное общение. У нас сейчас там накрываются столики на открытой летней площадке. Поэтому смело перемещайтесь, угощайтесь и, самое главное, общайтесь друг с другом на тему нашего любимого языка, любимой серии инструментов. Спасибо, коллеги, и до скорой встречи в ноябре. Спасибо.